we're going to talk about energy, and we're going to talk about power. With all of these equations here, we are going to be introduced to them today, and then we are going to be utilizing Ohm's law now until the very end of the semester, with I think maybe a week and a half where we're not using it. With energy and power, it's going to be brought up multiple times. However, it's always going to kind of be one of those things that gets tacked on that on the end. It's like, what's the energy of this thing or what's the power of that? So before we get into all of that, last time we introduced a lot of terminology. So we went through, we talked about electrons, where they come from. We talked about, in reality, we now know electrons are responsible for current, but with how we're going to go through and utilize our currents in this class, we are primarily going to use the conventional current, which is that positively moving charge. We also introduced the idea of voltage, which is going to have the SI units of volts. And we talked about the current being equal to the amount of charge passing per time. We mentioned resistance. We didn't talk about calculating it, but it is something that belongs to the material itself, or just we're going to be given primarily a value that we're able to go through and use. Any questions from last time? I know this looks like a lot of sections. I kid you not, for chapter 3, these sections here are basically algebraic rearranged versions of themselves. And it is a simple 3-term equation. So we're going to fly through the chapter 3 stuff. We'll talk about this stuff in chapter 4. And then next week, we will get into actual circuits where we start dealing with utilizing this and calculating values. All right, so we're going to talk about Ohm's law. We're going to constantly refer to it as Ohm's law. And what it's going to do is it's going to help us relate current, voltage, and resistance to each other. Now, something I want to be very clear. Ohm's law should not technically be referred to as a law. It's really Ohm's heavy suggestion. It works great for metals. It works great for resistors. However, when you start getting into things like insulators that have a voltage applied across them, not so much. So we're going to call it Ohm's law, but we should just acknowledge that it is not actually a law. So this is Ohm's law. It states that the current is directly proportional to voltage and inversely proportional to resistance. I equals V divided by R, or more commonly written out as V is equal to IR. So with this here, we want to remember our units. We're going to have volts. Current is going to be in amps, and resistance in ohms. So the symbols for those, does anybody remember what it is for volts? Yep. What about amps? A. I is for current, A is for amps. What about for resistance? In particular, it's capital omega. Little omega looks different. So, talked a little bit about the units for it the other day, but best method for finding ohms is it's just going to be volts divided by amps. Not its technical definition, but it is a definition. So what we want to go through and do is we just want to explore this a little bit, see kind of what's going on with Ohm's law. So before we do that, we're going to explore a basic circuit, but are there any questions on Ohm's law so far? So let's look at this circuit here. So if we look at our circuit, here we have an ammeter, which is going to read our current value. So this is going to be where we're calculating the current. Here we have a resistor that has a value of 10 ohms. And on the left side here, we have a battery. But with this battery, and anytime we see one of these lines passing through it, this means that it is a variable battery. So in this case, we have the control of it between 10 to 100 volts. So what we want to go through and do is look at what would happen to the current in this circuit as we would go through and increase the voltage from 10 volts to 100 volts in 10-volt increments. So if you just had to guess, right, again, we're technically utilizing Ohm's law here. So if I'm increasing the voltage, am I increasing, decreasing, or keeping current the same? Why do you say that? Don't want to call it power because that's a different term. We're putting more voltage into it. We are increasing the potential difference. If we think about it as a hill, we are making that hill taller and taller and taller. So you can go through. There's a 1 there. You can go through and you can go through and test this. Here we're assuming we have ideal wires which have no resistance in of themselves. And so as we increase the voltage, the only resistance we're going to have to care about is that resistance for the resistor. It's just going to be that 10 ohms. And if I take all these points and I plot them, I get a beautiful straight line. This, again, Ohm's law works great for metals, and it works fantastic for the standard type of resistor we're going to talk about in this class. So any questions before we do an example? This one? This is a variable battery. So anytime you see the arrow through it, that means variable. It's on top of the battery symbol in this case. Any other questions? So I want you to go through. There are 6 of you in this class, and there are 6 of these here. So we're gonna start. I think I've made the first row and the second row both do one before. So in the back, you guys are gonna do A and B. Up here in the front row, you guys are gonna do C and D. And in the middle row, you're gonna do E and F. If you are online, just pick 2 of your choice. And feel free to work with your neighbors and figure out what happens if this thing happens. So yeah, what happens to the current if this occurs? Feel free to discuss with your row buddy. Anybody want more time on number 1? All right, does anybody want to go first? Okay. Yeah, so right, you've doubled the resistance. In this case, for all of these, we are using I is equal to V divided by R. So if R is doubling, we are cutting in half. So how did you set that up? So you had, right, 1. So I is equal to R, sorry, V over 0.35 R. Is that how you did it? We think about mathematically setting it up. Does this make sense? Actually, let's ask the people who did B, right? Because this is a very similar one. B is reduced by 7, or is voltage instead. So not quite the same. B, did you guys write your equation out for? Okay. So in this case, right, 0.75. V, and so in this case, if I divide by 0.35, what does that get you? Right, because you're not in the case of this textbook, it didn't want you to put a percentage. It technically wants you to put a value. So if you divide by 0.35, what do you get? So your current is now up 2.85. What else? We got A, E, and F left. Yep. Yeah. Yep. So just triple the voltage, triple the current. All right. Middle row. What do you get for E? How'd you get quadrupled? Yeah. So you divide by a fraction. It's the same as multiplying by whatever's in the denominator. And what happened for F? Yep. Yay. Ohm's law is so fun by itself. All right. Any questions about 1? Yep. Current calculations. So we're going to do the next couple sections, which is basically how do you rearrange Ohm's law to find a value? This is how, if you need to find a current, you can use Ohm's law. I equals V over R. Right? If you go through and look at this, the thing that we will probably want to be careful with if we are doing a current calculation is our units. Typically, it's going to be the resistance that is the problem. So with the resistance that is going through and looking, we will have values that range from ohms all the way up to mega ohms throughout this class. It'll kind of somewhere in between. So we just want to make sure that our values are going to work out. So when I'm talking about the power here, I'm talking about what do I have? Again, typically related to the resistance. What type of ohmage do I have? If you want to, you can keep the prefix when doing the calculation and then kind of deal with it at the end. However, the problem that I noticed last year when people did that is they never went back and dealt with it at the end. So if you're more comfortable leaving it, you can. If you're less comfortable, don't do that. I recommend going through and swapping everything into either scientific or engineering notation. Then going through and doing the math, it is going to be a safer method. Any questions before we do another example. So this one here, we are being told to use a 5 rand resistor that's connected to a 12-volt source. The reason I put this example in here is for your quiz next week. This will be something I will tell you the colors for you to read it off of. It's not something you are expected to look at the colors and then try to figure it out. So we are determining the current of the color coded. It gives us the color code here. We want to find that current value. So let's go through and let's find that resistor value first. So first I want to go through and I have orange. So that is going to be a 3. My next one, I have violet, which is down here, which is a 7. Then I'm going up to yellow. And that is going to be a 4. So that is my first 3 bands. So if I'm looking at this table here, these are the first 3 bands that are coming down. So this section is the first 3 bands. This is it trying to explain to you what's going on with the bands. This is the 4th band multiplier. So in this case, we have gold. So we're going to have a 0.1. And then we have a 5th band, which is going to be our tolerance. So we're going to be within plus or minus, in this case, brown, 1%. So if we look at doing that, we have a 0.1 plus or minus 1%. So this is how we can go through and read this table in comparison to the one that's in the packet or a couple images ago technically in class. Oh, sorry. Sorry, the 4th band is a multiplier. I did that wrong. It's not a 0.1. The times 1. Look, something weird like that for it. Right, because it says 4th band multiplier, number of zeros following the 3rd digit. We have 1. Right, I wrote something down wrong on my notes. So yeah, so this is multiplier, number of zeros following the 3rd digit. Our 3rd digit was a 4. If I go through and look at my color here, it's gold. Point. Let me double check something really quick. What do you think I do with this tolerance? Why is it important that I have this tolerance value? Yeah. What else? Yeah, so technically with it, we can have 1% more or 1% less with that tolerance value. Okay, so with this 4th band multiplier, we take our original values. I'm going to multiply it by 0.1. And then I have a tolerance value of plus or minus 1%. That is how that was supposed to work. So our actual resistance value is going to be 37.4 plus or minus 1%. I need to find the current. So what should I probably be doing to figure that out? And what should my voltage value be? I have 12 volts. What is the correct resistance value to use? Is it? I'm asking you guys, what do I use? Do I need to take that 1% into account? Do I not need to? What should I probably do here? I do not have to account. So this is exactly 1%, so that it has an infinite accuracy. So I don't want to round it to 1. Yeah, so in this case, I'll have 2 sig figs because of my 12-volt source. But do I need to take that percentage into account when I calculate the current? Yep. So if I want to get the range of the possible current values, to go through and do that. So I'm going to have an I max, and I'm going to have an I min. I'm going to have a 12 volts divided by. So there's a couple different ways that you might be more interested in plugging this in. I personally, when I'm dealing with a percentage, like to do the 0.0, like the 1.01, just use that to multiply by the number. So my 337.4 ohms. And this is technically ohms. This way, I don't have to take the original value, then add 1%, and then go through and do my division. Same thing is true with the minimum. In that case, I'll have 0.99 times my 37.4 ohms. So to 2 sig figs, what should I have for my max? You said what? Okay. That is in. Okay. What about I min? So in this case, because it's a tolerance of 1% and we have a relatively small resistor, they end up having the same value in this particular case. When you would deal with larger resistors, so we're looking at like mega ohm type things, even a 1% can have a large difference in that current value. Questions about 22? The resistors we're going to deal with in this class are both directions. So that this is the current that is, sorry, let me back up. With this current here, we are assuming a single source from the battery, a single resistor. So in this case, the current's the same everywhere, but that's our problem for next week, not right now. Otherwise, this would be the current through this resistor. Any other questions on 22? All right, voltage calculations. You rearrange Ohm's law to be V equals IR. Again, with this form here, this is going to be the version that we see a lot in over the next couple of weeks. And by the next couple of weeks, I mean the entirety of the semester, where we are looking at it in conjunction with Kirchhoff's loop law, which we will talk about later. So just understand this is going to be the most common version that we use. Any questions before we do an example? Yeah. How do we solve 31? Yeah. And V equals IR. I'm going to take my current value. Right. In this case, I had to read the number 3. It wasn't shown as a number 3, so I had to sit there and process it for a second. 3 amps, 27 ohms, 81 volts. Any questions about 31? How do you think we solve for resistance? Yay. R over VI. We are never going to calculate in this class resistance through resistivity. So if, pretty sure. So if you have the packet, the last, there's an optional example for the last 2 pages. This shows you where resistance comes from in wires a little bit. We're never going to do this, which is why this is an optional example. This is kind of a exploration as to why we're ignoring the resistance for wires and why we will just be using the resistance value from our resistors. So if you, for some reason, need to calculate a resistance value, it's going to be going through and doing it this way. So any questions before we try it in an example? Okay. So 36, we're going to use R equals IV. What do we want to think about before we solve this one? Okay. So I have a prefix on my current. So I'm given 2 milliamps. So do I want to keep it as milliamps or do I want to deal with it now? Okay. You can keep it. What is my V value? My voltage. Okay. So I'm just going to take those and plug it in. I'm going to have 2 milliamps divided by 6. Sorry, I wrote that upside down. Right, it's V over I. Oops. 6 volts divided by 2 milliamps. If I go through and plug this in, I'm going to have 3 volts per milliamp. I would like to convert this in my units. So now I don't need to worry about the 3. Now I need to try to figure out how do I get this into some form of ohms. So I need to move that prefix in the denominator into the numerator. So milli is 10 to the what? Okay. So I have 10 to the, I'm dividing by 10 to the negative 3, which is the same as multiplying by what? So I have 3 kilovolts per amp. Or how else could I write that out? Three times 10 to the 3 volts per amp is our ohms. And if we wanted to put a prefix on our ohms here, what would it be? Yep. So 3 kilo ohms, 3 times 10 to the 3 ohms. Same idea, regardless of which one we have. Any questions on 36 or Ohm's law in general? Yeah.
Have the denominator normal. You have to change the prefix on the.
Convention.
So is that just the rules always?
That's just the rule because somebody decided that it looked prettier in the numerator.
Unfortunately, on the quiz, I like don't understand this at all. I feel like I should, but okay, that makes more sense.
It's a choice. I mean, right, technically, all three of these are the same.
Yeah, that's kind of what my thought was, but
The goal though would be to try to get it into some form of ohm. And so the reason right, ohm is the more acceptable way to write out the value. To get to ohm, we need to divide by amps.
It is putting 3,000. Steps. But it has three. There's 3 times 10.
Yep. Yep. Many ways you can write it out. Again, this textbook's going to ideally want you to do 3. I will ask you to 3 to 5 is fine, unless you're told less. Yep. Any other questions about Ohm's law stuff? We're done with chapter 3. We're going to go on to chapter 4 now. So this, again, with the chapter 4 stuff that we're going to talk about here, these are terms that are kind of technically being utilized in the background for a lot of the questions that we're going to be seeing. So when we get into Kirchhoff's laws, in particular Kirchhoff's loop law, or I forget what it's called in this textbook, whatever the one it is. Technically, it's a statement of the conservation of energy. So we are talking about energy without directly talking about energy. We're going to introduce energy and power now. However, we're not going to use them all the time. So energy is defined as the ability to do work. It is the ability for us to move a charge that doesn't want to be moved from one location to another. That is what it is. It has the SI unit of the joule. Power is how fast you are using that energy. So here with the general definition for power, it's work per time, or you can use energy per time. And it has the SI unit of the watt. Does anybody know the imperial unit for power? The word power is in it. And an animal. It's horsepower. 1 horsepower, which is abbreviated as HP, is 746 watts, and a horse does not have 1 horsepower. It's something like that, yeah. I think it's 7 to 10, depending on breed. So, somewhere along the line, somebody made a choice. And I'm going to be honest, horsepower, probably one of the dumber ones. It's not, but it's up there. So with circuits in particular, we typically do not see joules utilized. It would be a lot. There would be a lot of joules for the amount of time that you typically have something on. So if I look at my units here for power, it's going to be in watts, which is a joule per second. If I want to take that watt and can have it related to an energy, what I would need to do is energy is equal to power multiplied by time. So for the units, I would have watts multiplied by some amount of time. How many of you get an electric bill or have seen an electric bill? What do you typically get charged with respect to? You guys know what it is? Bless you. I get charged kilowatt hours. So the kilowatt hour is a measurement of energy, not of power. And this is very confusing because how we use energy and power in conjunction with electricity in our day-to-day lives is roughly the same. So we're going to talk about the kilowatt hour on the next slide as well. But any questions so far? All right, so when we talk about energy, again, we're going to see the kilowatt power, and we're going to always talk about it as the amount that is being consumed. How much has been consumed by this resistor, this light bulb, this whatever it happens to be. So if we're looking at the textbook, it's going to use W instead of E when it's talking about it. Drives me up a wall. That's a different problem. But we're never going to really see it like this. The reason we use kilowatt hours, again, is the joule is impractical. It is a relatively small value in comparison. So when you're using electricity over the time span of a month, you're going to be dealing with very, very, very large numbers. And as we talked about a little bit last week, human brain's not very good at understanding how big things are. So the kilowatt hour is a fantastic way to go through and just kind of take that number and make it mean something to us. So for the kilowatt hour, it's 1,000 watt hours. The technical abbreviation is K for kilo, capital W for watt, lowercase h for hour. So when we see powers, we are going to be seeing the kilowatt hour utilized. However, for small circuits, so when we're talking about just taking volts and multiplying it by amps, so if I just take a volt times amp, this is going to get me watts. So V times A equals W. When we're talking about units, not when we're talking about symbols for things. So here, volts times amps will get us watts. Sometimes we'll have to go through and then figure out if it runs for this many hours, how many kilowatt hours do you then have? Units for power and energy in circuits, kind of all over the place. And I apologize for that. Any questions so far? So how we are typically going to use the power equation is not with the couple of equations that we've seen here. More often than not, we're going to be looking at how does a resistor consume power. So here we have one of the three definitions for power, where power is equal to the current squared times the resistance. So this tells us that for our particular resistor, we take its value, we multiply it by the amount of current passing through it squared. That is going to tell us what its power is. Maybe though, I don't know what the current is. Or maybe I don't know what the resistance is. What can I use in conjunction with this equation here to get power written in two other ways? Talked about it not too long ago. If I want to get rid of resistance, what can I use to do that? Ohm's law. I can use it in two different ways, and I can get these two other equations as well. So here I have power is equal to voltage times current, or voltage squared divided by resistance. All three of these are equally referred to as Watt's law, and they require basically stuff to be an SI technically to go through and have it pop out in watts. So again, whatever you're more comfortable with doing, you are welcome to do that. Typically, with our values when we're calculating power, they're all going to be in SI anyway. So there's no need to change them and change that stuff around. So these are the equations I would consider looking at for calculating power. Any questions about power before we do an example? I want you to briefly discuss with your neighbors which of Watt's laws is going to be the best for 19 here. All right, which forms the bestest for 19 here? You guys agree? Why'd you guys pick this one? I have the volts and I have the current. I don't need to do any algebra, just plug these guys in and multiply. So what should my voltage be? My voltage is 3 times 120 volts. And what's my current? What's 120 times 3? Excellent. 360. And then what should this pop out in? Watts, which is in W's. This is pretty much the extent of how we will be using power in this class. So basically, a lot of the questions you'll see in the textbook, they'll do a bunch of, like, part A is going to be hard in comparison to B. A is going to be like, find the current through all the resistors. Then B's like, what's the power consumed by every resistor? Right, in that case, you probably want to use a different power equation, but you could go through and use this one. You would have everything for it. So we're going to kind of deviate a little bit, and we're going to kind of talk about just some circuit stuff to go through and kind of understand what's happening in a real circuit more so than, right, these just kind of random numbers as they've been right now for power. So first, we're going to talk about power, resistor power ratings. Apparently I've been wrong. It's not 40 degrees, it's 70 degrees. My bad. So the idea is that every resistor has some max amount of power it can safely dissipate. If you start exceeding that, that's going to be where your resistor starts smoking, catches on fire, shorts, depending on the type you have, depends on what it does. More often than not, it is something that is determined by the physical size of the resistor. So some of you handled some resistors yesterday in lab. Some of you have been handling them at home with renting out the lab kits. Those resistors are pretty small. You can get resistors with the same value that are much larger. So those would have typically a higher power rating because it's related to the length times the circumference. That is a rough approximation for what it is. However, were the resistors you guys used yesterday perfectly cylindrical? Yeah, they were a little bulbous on the edges. So with that, right, that would be that does affect the calculation roughly. Again, we're not going to really care about it in this class, but understand that that is something that's there. Most resistors have a power rating between 1/8 of a watt and a full watt, and this is specified at 70 degrees Celsius. Once you start getting above 70 degrees Celsius, that is where you start having some problems with your resistors. So not with the values we're using in this class, we're not going anywhere near failure for the resistors. For the lab you guys are going to do next week, you do have the ability to set it up such that they'll catch on fire, but it's a simulation, so I'm not worried about it. But just understand that that is something that is technically going on if you're dealing with electrical circuit design. You'll need to figure out sometimes, can my resistor carry this current through it or the load through it if, it's this big. With this power consumption, right, this is again the amount of energy we are using per time. So I want to go through and I want to talk a little bit about energy conservation in a real circuit compared to the circuits we're going to deal with for the rest of the semester. So before we do that, any questions so far? And I really did a great job animating these last slides. So, right, power is going to be consumed. So we'll talk about it a little bit soon. We're going to look at energy being 100% conserved and doing it the nice, easy way. In reality, as we go through and go around a circuit, we are losing some amount of energy into the environment, where the environment is everything except the circuit itself. And so when we go through and have that, the power that we're using is technically a little bit different in comparison to just having the equation that we talked about a couple slides ago with Watt's law. So let's look at the picture. So here we have our conventional current. And here we're talking the electron current. And then we'll do conventional from chapter 5 on. So here we have our charges coming out of the negative side of our battery. And based off of our color code down here, that is where it's going to have the most energy. Here we are treating our wires as ideal. So there's no resistance across the wire. That means that from the battery to the resistor, there's no change. We're treating that as if it's ideal. As you go across the resistor does start to heat up. And with that, it's going to start heating the air around it. So with this heat that we're getting out of these resistors, this is energy being lost to the environment. Which again is just everything that's not our circuit. So we can see as we go around our circuit here, it's representing it in the middle of every resistor. Is it the exact middle? Who knows? But how it's being represented is I'm losing some amount of energy, and that's being done to heat to the environment. So this is something that happens in real life, in reality as well, right? Your wires do heat up. So there is more energy being lost, but typically that energy that's being lost inside the wire is much smaller than that of the resistor. So it, again, it's typically ignored. However, is something that if you really needed to go into it, it would be of importance. As we go across these resistors, not only are we losing energy into the environment, this is going to be where we start seeing voltage values change as well for our charges. And that's what we're going to focus on next week. To start figuring out how does that voltage behave as we go around the resistor. What do you think happens if I look at the conventional current instead? What if I looked at the positive charges moving around the circuit? Where would the high energy be? Why did you say it was here? You're right, but why? Yeah, it hasn't come into contact with the resistor yet. You have the highest energy because you just left the battery and you're going along an ideal wire. There's no change in your energy yet. You're going to hit this resistor and you're going to have medium energy. And then you're going to hit that last resistor and then you're going to have low energy. So the same behaviors are happening, it's just happening in the opposite direction. So again, with the conventional electron currents, mathematically, they're doing the same thing, just the order is going to be flipped. We'll see some more of that, like I said, next week. Questions about energy conservation. So we're going to talk about Kirchhoff's voltage law very briefly today, because we want to starting to understand what's going to happen in our circuits. We will spend a lot more time on this when we go through and start dealing with on Tuesday. We're going to come back. We're going to talk about what does a loop mean in a current or in a circuit, kind of going through some more detail for what that is. But the main idea of Kirchhoff's voltage law is that if I start and end at the same point in my circuit, my change in voltage is going to be equal to 0. So we are going to be going through and assuming that as I go through the wire, I'm not losing any voltage. I'm only going to be changing voltage anytime I have a circuit element inside of my circuit. So that's going to be my batteries, my resistors, when we get to them, capacitors and inductors. Those are going to be the only things that affect voltage for this class. So do you think that from a battery, right, do we think that's going to give or take voltage? How do you say give? That's your power supply. It's going to give you voltage. So we're going to gain voltage. So let's read the sentence, and then we're going to put a little asterisk next to it, usually. We gain voltage from our power sources, and we lose voltage as we go across our circuit components, usually. There will be times, and we'll talk about this soon, where depending on how we put our batteries into a circuit, they don't always add up together in a positive way. This is normally it's true, but not always, and we will build up those situations as we work our way throughout the class. This was the one that I will probably call the loop law all semester long because that's how I learned it the first time. Means the same thing. Loop law goes around a loop, looking at the change in voltage. This textbook calls it the voltage law because you're focusing on the voltage. Same thing, same rules. I will screw up these names all the time. So we're going to do one last example. And for this one, there's no math. We just want to try to figure out how can we sum up some values to 0. So before we do that, any questions on Kirchhoff's voltage law so far? So let's talk about these circuits before we go through and attempt to do 30 here. So you will find that the textbook is going to love to draw its circuits looking something a little bit like this, where we don't necessarily have a wire connecting our two sides of the circuit. So if I look at this first one here, what I have is I have a ground. This is something that's typically just shoved into the physical earth. I have a battery. So with it, I have my negative and my positive sides. I then have a wire going over here to the resistor, and then this resistor is also going into a ground. If I try to create something like this in reality, what's going to happen is all my current, and if I'm using my conventional current, this goes like this. Goes from the battery through the resistor straight into the ground. That's not a very interesting circuit. And the same thing is true with B. In B's situation, if I'm looking at the conventional current, the way it's drawn is I'm just taking all my current and putting it straight into the ground. Again, not very interesting. So with this type of circuit, you're kind of supposed to understand that there is a wire here that is going across. And if something bad happens to this wire, then things go into the ground. So when I give you guys circuits that I'm creating, so this will be on your quizzes and your exams, I'm never going to leave them open like this because it drives me up a wall. I think it's weird. However, this is something that electrical circuit diagrams do in this textbook, some other textbooks, but not all of them. So I don't understand the rhyme or reason behind it, but just understand that if you see something open like this, just draw that imaginary wire across to complete that circuit. So what I want to go through and do is let's start with A, and then I'm going to have you try B and C, is I want to look at the conventional current. So if I'm going, I need to pick a starting point. Personally, and something that you're going to see ourselves do a lot as we work our way through the semester, is we like to start by the negative side of the battery. Because this is a nice place where you have 0 value related to the voltage. I'm next to a ground in this particular case, so if something wonky has happened, everything's dumped into the ground. I don't have to worry about it. I then want to look at the direction of the conventional current that's going to come out of the positive side. And because I'm going from negative to positive, I am going to gain this voltage. And I'm going to keep going along my ideal wire here. And then I'm going to go down through the resistor. And then I'm going to go back to my original location. Just gonna go around in a loop. For this loop, delta V has to be equal to 0. So if I am gaining voltage as I go across my battery, what should I be doing with my voltage as I go across the resistor? I should lose it. So I need to lose voltage. If for this battery, I went from negative to positive to gain, and I'm losing it over here, should I be going from negative to positive or positive to negative? Right? I want to do the opposite of what I did for the battery. I go from positive to negative. So again, we'll talk about this more next week. For some reason, it introduces half of it here in chapter 4 and then introduces it more in chapter 5. So that's why we have that weird little subsection of chapter 5. I want you to try B and C. Try to figure out which way should it's called the voltage drop or the polarity of the resistor be, and feel free to work with your neighbors while you do so. Anybody want more time on 30? All right, so somebody want to explain to me what they did for B? Yep, so it's just going the other direction, so we can just flip that around. What about C? How do you know which side is the positive side? Okay. So how'd you put, what side did you put the positive on? Oops, sorry. I also, you told me the right thing and then I heard that. Yeah, so I have positive here, negative here. For this particular type of circuit, what do we notice about the positives? Think about it if you're the proton, so the positive charge, right? You're going from negative to positive and then positive to negative. So the positives are lining up with each other, right? You're doing positive, positive, negative, negative. This will not always be the case. So we're going to talk about, again, this is sometimes referred to as polarity for the resistor. We will talk about this a little bit more next week. However, in the future, I'm going to teach you how to figure out if it's positive or negative without having to sit there and think about it for more than 2 minutes. So there are some shortcuts. I will teach you those shortcuts, but we need a little bit more background before we get there. Any questions on 30? So one last thing, promise it'll be quick, and that is just going to be power supply efficiency. Moving forwards, we are going to assume everything we deal with is essentially ideal when it comes to a source. There will be a time when we talk about the parallel plate capacitor where it's not ideal, but mathematically it's going to be ideal when we deal with it in a circuit. Same thing is true with resistors, inductors, and batteries. We just want to acknowledge that we are making the assumption that everything is perfect when in reality it's not. In reality, the power that you get out is going to be less than the power that you put in. Your efficiency is less than 100%. So output is always less than the input thanks to the second law of thermodynamics. So just understand that we are making a ton of assumptions across this class. That's what this slide is here for. We're going to be assuming ideal wires, which have no resistance, no change in voltage, none of that stuff. In reality, we would have a changing voltage. We would have, some resistance in our wires. We are going to assume our power supplies are 100% efficient. In reality, right, batteries go dead over time. We're going to pretend that that does not happen. For our resistors, we're going to pretend they don't heat up. They do, but we're going to pretend they don't. So we're making a bunch of assumptions such that we can make the math as simple as possible to explore the key concepts, but we're not 100% accurately explaining what is going on. So any questions about today's material? Yeah. Currents, so the current value is the same, but the any other questions? All right, I will see you on Tuesday.